We move to part 5, some conceptual points raised in the debate by Aram and others. So here is a taste of the discussion. I should say that I personally am very interested in internet research activities in mathematics and both pure mathematical questions and application of mathematics to other areas. And there are a lot of arenas for that recently, and this is a fairly interesting topic. And here is a taste from the discussion, and this is a comment by Peter Shaw. Peter said that the difference between 1 star and 2 star, where 1 star represents my models, is that in 1 star the universe need to know what code you are using in order to follow. This attributes both more intelligence and more malice to the universe that I am willing to believe that it has. So, in other words, what Peter says, it takes too much malice and intelligence for nature to detect and intercept the quantum error correcting codes. And this addresses, for example, my first conjecture, which says that the noise is aligned with the code. You will have mixture of undesirable code words. Now, the mistake is again the trivial flaw. Peter takes for granted a general purpose device. Now, if every quantum code requires a special device to create, then no malice and no intelligence are needed for the universe to intercept them. The property of the noise will just be will be determined by the device, which is determined by the error correcting code. So there were quite a few very interesting objections and comments in this almost year-long debate with about 1,000 comments. And here is a list of few of them. So Aram Harrow raised the following point: if quantum fault tolerance is impossible, why classical fault tolerance is possible? And I must admit that I also regard classical fault tolerance as possible. Aram raised another interesting point. We can redefine the quantum system to include the environment. So we can make the noise, we can just declare the noise as part of the music. Right? So then everything will be just pure music. And this was a very interesting comment, and we had about 60 comments around this idea. Very nice thought experiment to add to the computer also everything around it. Chris Moore opined that skepticism of quantum computers means skepticism of quantum mechanics. Joe Fitzsimons raised the issue of blind computation. This is a form of quantum computing where the state of the computer is actually a maximally mixed state. So you cannot know anything about the computation. John Preskill mentioned a general model where the threshold theorem holds. And he actually presented the paper while we were discussing. Joe again raised a two-locality argument. And more generally, he claimed that the conjecture are in conflict with the principle of locality, which is an important physical principle. So I will mention a few of these things. I should mention about Aram idea to redefine the quantum system to include the environment. So we had, as I said, we had a long back and forth discussing about it, and at the end Aram admitted that the only way to really do it is to let the system be the entire universe. And I don't take argument from the entire universe, so it doesn't work. Okay, here's an extremely important point. This was Aram's first post, and the title of this post was Flying Machines of the 21st Century. So this was a balance to the title of the first post, which talked about perpetual motion machines. And every post in Lipton and Reagan blog has a sort of a saint patron saint, I don't know precisely the way. And here it was Dave Bacon. And the point of Aram was that how is it possible that classical computers are possible and quantum computers are not possible? And this was one of the main topics of our debate, and 20%, maybe 20% of the entire discussion was devoted to this important point. And I don't want to discuss it too much in this lecture. I just want first to make again, using our picture, that the important point that general purpose classical computers are actually special purpose quantum devices. So general purpose classical computers, they don't belong to this uncharted territory of universal quantum devices. As quantum devices, they are still very special purpose. And I think roughly speaking, when we talked about this issue, I think this is a major challenge, not only for quantum computers skeptics, but also for quantum computer researchers. What is the distinction between quantum computation and classical computation? This is a major distinction in our world, even if quantum computers can be developed. And we mentioned several things. We mentioned the repetition mechanism, which is essentially the basic mechanism which allow out of this chaotic, noisy world to create robust information. And this repetition mechanism is something which applies, which create classical information, but it does not allows for quantum information. And we also discussed that, for example, the first conjecture about that mixture, that every implementation of quantum error correcting codes, the code word, what you will actually get will be a cloud, a mixture of the intended code word with unintended code words. This conjecture still allow to have very robust classical information. You can have one such cloud around one point in the Bloch sphere and another such cloud around another point, and this will be a very robust classical memory, but it will not give robust quantum memory. And we also put another important point is that the classical memory is also robust to various types of correlated errors. But this is, as I repeat, this is a major challenge both for skeptics and for believers, and there is a lot, I think there's a lot to be learned in this point. We move to another point, locality. So there was a claim that the conjectures and noise models are based on non-local noise, which goes against known physics. So again, one of the participants, Joe, he raised a particular technical point, which he called the two-locality, and then we dwelled on it for maybe 40 or 50 comments, and then actually by another participant, by John Preskill, it turns out that his specific suggestions was incorrect. But I think the crux of the matter is different, and let me point it out. When, in my opinion, when your model imposes strong locality on the noise, it allows fantastic non-local behavior to be demonstrated for the signal. And a correct approach for modeling noisy quantum systems will have locality emerged from the model, both for the approximated unitary evolution, the signal, and for the nature of the fluctuation, which is the noise. So the difference, the conceptual difference between my models and the standard models is that locality will emerge from the model rather than being imposed on the model, which allow this fantastic non-local behavior. Okay, here's another question. If computationally superior quantum computers are not possible, does it mean that in principle classical computer suffices to simulate any physical process? So this is a question that was raised several times, and it is a very important question. It's not entirely fully defined, but it is an important question. And here's the short answer. The short answer is yes. So the short answer is yes. Of course, if you want to make a long answer, then things get a little bit more complicated. And the point is that computational complexity is not the only obstacle for making simulations. In order to make simulation, you need to have the information, you need to have the understanding. And in principle, when we talk about simulation, it makes sense only for robust physical processes. For physical processes that we can repeat and get the same result, whether it's deterministic result or stochastic result, but simulation only apply for robust processes. If we have a process which is not robust, then there is no way to simulate it, and this is an obstacle which is not computational complexity obstacle. This is a deeper, a wider obstacle. So we don't have, even on the information theoretic level, we don't have the information to make a simulation. So we talk about robust physical processes, and here again I think yes, indeed, if computational superior quantum computers are not possible, then this will be possible to do on classical computers. Of course, even for completely classical computation, sometimes you need understanding in order to be able to simulate. Or on formal ground, sometimes your simulation depends on knowing some secret. So we see it in complexity. There are cases where we know that the process can be simulated in polynomial time, but if you don't know the key, then you cannot process it effectively. Does the impossibility of quantum computers means breakdown of quantum mechanics? And again, the short answer is no. So what's the big deal then? Suppose that you accept that indeed the trivial flow can be devastating and may cause quantum computers to fail. Will it have any additional interest? Of course, it will be very interesting to know that, but so here is an analogy which is sort of nice, and the question is, what was Lord Kelvin's mistake in dating the Earth, which he did repeatedly during his glorious career at the end of the 19th century. So Lord Kelvin was perhaps the most famous physicist in the second half of the 19th century. He was a great physicist, and he dated the Earth, and he determined the age of the Earth to be somewhere between 20 million years and 100 million years. And his mistake is about a factor of 50. We know by now the age of the Earth fairly accurately. It's about 4.6 billion years. So what was his mistake? Usually when I give this lecture and I ask this question, several people come and say radioactivity, which was my answer before somebody told me that this is not the right answer. And the answer is not radioactivity. Of course, radioactivity would be sort of understandable because this was not something that was even known at the time of Kelvin. But Kelvin's trivial flow was to assume that heat conductance is the only mechanism for moving heat around. So, and actually there is another mechanism, which is something that we know from home cooking, that when we cook something, then hot material, when we move it around, is also a way to move heat around. And this accounts for most maybe 95% of the error. I mean, radioactivity or nuclear processes have some importance, but this is the main thing. But Kelvin's mistake is also related to deeper issues. And Kelvin dated the sun before dating the Earth. And there his estimates didn't take into account nuclear reactions. In the case of the sun, he couldn't know the correct way to date the Earth, to date the sun. But when he dated the Earth, he made the correct hypothesis that the age of the Earth is roughly in the same ballpark as the age of the sun. So his mistake in dating the sun inflicted on his expectation in dating the Earth. And his estimates for the sun didn't took did not take into account nuclear reactions, unknown at the time. And so this is a very interesting story. So on the one hand, he had some trivial flow that he could anticipate it, but this was really related. And this trivial flow is also confusing what are the variables and what are the constants. So if you want, it's a little bit related to our story. But there were various deep issues of physics that he couldn't know. In any case, whatever you say about Kelvin, he was dating the two superstars of our solar system. I should say that I gave this talk several times, and usually people are quite satisfied by this explanation, but there were two cases that people asked me, okay, but why this make the computation go in the way it goes? Why this convection or this material moving around make the computation 50 times larger and not smaller? And indeed, it's not so. For this, you have to go in more details to the details of Kelvin's idea. And he had a fairly clever ideas of dating the Earth. Actually, the fact that he dated the Earth, the fact that he thought that the scientific methodology is the right thing to date the Earth, this was already quite an important step. And there were people in his time that thought that the Earth exists forever, or that this is not a scientific problem. In any case, if you want to understand it, you have to read the very details, and actually you can find them. You can find a link to the paper on my blog. So, to what areas of physics are obstructions or impossibility of quantum error correction relevant? So, understanding the quantum fault-tolerant barrier may have important connection to thermodynamics. Well, this is the most natural thing. Thermodynamics is the study of noise in quantum systems. So it is very. This is a very basic. This is the most the physical theory which is most related to this issue. It also can be related to approximations and perturbations methods in various areas of quantum physics, including quantum field theory. So noise and approximations, essentially, it's two similar things. And to understand the art of approximations in quantum physics is extremely important. And our questions have bearing on this topic. And the last, quite surprisingly, is that this may have some connection with classical physics. And there are possible connections between quantum noise and symplectic geometry. And Leonid Poterovich studies similar connection in recent papers, which are very interesting. And actually with Leonid and Guy Kindler and Dorita Aronov, we try to study discrete time versions of the smooth Limland evolution, very simplified case, and to see the connection with several of the things that came in this theory. Okay, so let me move to the sixth part, which is a short part, and this is about quantum computation without quantum fault tolerance. So I try to draw formally the quantum fault tolerant barrier to describe the distinction between quantum systems which have quantum fault tolerance, which invoke quantum fault tolerance, and quantum systems without quantum fault tolerance. But maybe you can get computational superior speed up without quantum fault tolerance. And if you think about it, to address the question if fault tolerance is needed for computational speed up, you need to formally define what is fault tolerance, and this is what I'm trying to do. So you need, the distinction I'm trying to do is necessary even if you just want to understand on formal ground the question, is fault tolerance needed for quantum computation? But there are suggestions to avoid fault tolerance in quantum computations. And let me mention three such suggestions. One is a topological quantum computing. And topological quantum computing does not avoid quantum fault tolerance altogether. And you see here, well, you don't see here, but you see in the picture that it's more or less on the boundary. But the idea in topological quantum computing is that you can take physical gadgets that will implement the quantum fault tolerance in a similar way to the way that memory, digital memory work. So once you have these physical gadgets, then you don't need to implement fault tolerance in the software. So this is one idea. Another idea is a company called D-Wave. So they are actually building quantum computers, and there's no claim that there is any form of quantum fault tolerance. And there is certainly hopes by the D-Wave people that their computers can achieve a computational speed up. So I don't have much to say specifically about D-Wave, but I want to point out that D-Wave machines are based on a notion called quantum annealing, and there is an even larger notion, very important notion of adiabatic quantum computation. And the study of noisy adiabatic quantum computation, and in particular examining my conjectures, about noise for adiabatic quantum computation, is a very interesting project. And a third very intriguing idea is the idea of boson sampling. And let me, in a few slides, just say something about this idea. So let me describe to you what are permanent machines. So permanent machines are hypothetical devices with the following properties. The input is an n by m complex matrix whose rows are unit vectors. So you start with an input which is an arbitrary n by m complex matrix. Now the machine creates a probability distribution that produces multisets of size n for 1 up to m. So there are m plus n minus 1, choose m such multisets. For every such multiset there is a permanent. You take and the probability of a multiset is proportional to the square of the absolute value of the associated permanent. So we already talked about it when in the very first part of the lecture, that to compute permanent is a very difficult question. It's a number p. Even to approximate a permanent in this setting of complex numbers, it's a number p. So it means that it's much beyond the NP complete, or at least as far as our picture of the computational hierarchy is concerned. And it's very difficult, and yet, so permanent machines do something quite miraculous. They sample subsets according to the value of the permanent. And the quantum computer, this is a surprising fact, that a quantum computer with quantum fault tolerance, so if it's a noisy computer, an ideal quantum computer, or even a noisy quantum computer with quantum fault tolerance, can achieve this task on the nose. So you can do it with quantum computers. And this is in spite of the fact that quantum computers are also believed not to be able to compute permanent. So nature cannot compute permanent, but nature somehow can sample submatrices according to the precise value of their permanent. And I would say, as an aside, that this gives a strong reason to doubt that quantum computers are realistic. Well, perhaps one anecdote. So of course the connection between permanents and certain types of particles called bosons, and between determinants and fermions, are of course known before quantum computers. Certainly in the early days of quantum computers, people looked at it from various angles. There is a nice story that Avi Vigderson once gave a talk about the properties, how hard it is to compute permanent, and then Tali Tishby make a joke that the task of the bosons, which compute permanent, is much harder than the task of the fermions, which compute determinant. And this is a nice joke, although Tali also made the point that in nature we don't see such a sharp, we don't see any trace of this huge computational differential, computational complexity distinction between determinants and permanents. So here is a recent, of the last few years, suggestion by Aharonson and Arkhipov, which is called boson sampling. So they wrote a paper and they make the following 4 points. First point is that classical computers cannot serve as a permanent machine unless the polynomial hierarchy collapses. So this is a nice theorem, and it really shows that permanent machines represent a superior computational complexity. It gives a very strong evidence for that. The second point is that it is plausible that we can achieve without quantum fault tolerance approximate version of permanent machines. So perhaps this is the suggestion. We can build a machine based on photons or some other gadgets that will achieve this task approximately without any quantum fault tolerance. The third point they make is again a computational complexity conjecture that says that classical computers cannot serve even as approximate permanent machines, even in the cases where their proposal for approximate boson sampling applies. And then comes the punchline. And the punchline of Aronson and Arkhipov is that by building approximate permanent machines, we will demonstrate quantum speedup without doing anything useful. So this was sort of a nice point. It's sort of a nice conceptual idea, and we can ask what's wrong with this idea. And what's wrong with this idea is essentially the point number two. I mean, there are some issues with the computational complexity conjecture, but the main point is that in point number two, when Aronson and Arkhipov say it is plausible that we can achieve without quantum fault tolerance approximate version of permanent machine, this should be changed to it is implausible that we can achieve without quantum fault tolerance approximate versions of permanent machine. And this is related to a theory and to a recent project based on a theory that I developed with Itai Binyamini and Oded Shram in the late 1980s, and it's related which make the distinction between noise stable and noise sensitive process. So it turns out that permanents are very noise sensitive. It means if you take a random Gaussian matrix and you add to it a random Gaussian noise, then the value of the permanent will not remember at all the value of the original matrix. So the noise will take over the matrix in a very strong way. And this means that undesirable mixture will prevent good approximation in the proposal of Aronson and Arkhipov. Okay, so we move to part number 7. Reasons to disbelieve, experiments, and summary. Okay, so this lecture. This lecture proposes an answer. So I should say this filming is taking place in the studio, and my audience consists of Tzlil Shram. So Tzlil is Oded's daughter. So it was great for me to have this semester in Berkeley with Tzlil and Tynan being in town. And also thanks for taking part in producing this. Of course. Okay, so let's move to the last part of the talk, which is reason to disbelieve, experiment, and summary. So this lecture proposes an answer for why quantum computers cannot be built by showing a logical flow leading to the common incorrect intuitions, and by offering alternative modeling for quantum noise. But it did not address the question, why should we believe that quantum computers are not possible? Why should people prefer my convoluted noise models, which are really literally convoluted, over the standard noise model, which are admittedly the most natural way to try to model noise. And indeed, when we started our debate, Aram asked me to explain my reason for believing that quantum computers are not realistic. And at the beginning, as a mathematician, I found this question a little bit strange because, I thought that we should explore both directions, and the possibility of quantum computers is a great opportunity that we should explore. And the impossibility of a quantum computer is also a great opportunity that we should explore. And I think that quantum error correction can play a role in both this exploration. But Aram really made the point that he would like to understand my reasons for thinking that quantum computers are implausible. And I made an effort to collect together the fantastic way that quantum computers will change our reality, which make, in my opinion, quantum computers implausible. And this has led to a whole separate post in the debate whose title was, "Can you hear the shape of a quantum computer?" So here is the picture of the post. You can see here, or you can see, almost see here, the picture of Mark Katz, who is famous for asking the question, "Can you hear the shape of a drum?" And in this post, I raised several points where quantum computer will change our reality, and it's more believable that we will need a moderate change in theory than such a drastic change, than we'll witness such a drastic change in reality. And here are some of the reasons. So the first point is of course just this. So how quantum computers will change reality? So the first point is that a universal machine for creating quantum states and evolution could be built. This is very far from anything we witness now in both in natural and in synthetic quantum evolutions. Complicated states and evolutions never encountered before could be created. The third point is that states and evolution could be constructed on arbitrary geometry. And this is a very important point. So in real life, there seems to be a strong connection between the geometry and the physics. And somehow quantum computers will break this connection. You will be able to simulate any quantum evolution on any type of geometry. I think one example I brought in this post is you can consider Kitaev's four-dimensional surface code. And we will be able to simulate them on a quantum memory whose shape is the letters IBM. And then a similar thing can be said not only about the geometry, but about time. Emulated quantum evolution could always be time reversed. If you can run an evolution backward, you can also forward. You can also run the same evolution backward. Again, this is different than our experience for quantum evolutions. Of course, it's not different from our experience from computers, from classical computers. And as a matter of fact, not only time reverse, we can make the permutation of time in any way we want. Like, for example, this we can do in the classical world. For example, the order in which you will see this video is not necessarily the order in which it was taken. And as a matter of fact, you can detect the discrepancy by looking at my shirt. Everything which was taken yesterday, I had a white shirt with jacket, and everything which I had today, I have a gray shirt. But beside that, we can reverse the order in any way we want. And again, this both time reversing and the time permutation is go against our experience for general quantum evolutions. Another point is that the noise of approximately pure quantum states will not respect symmetries of the state, but rather depends on a computational basis. Again, this is very different than the way we witness quantum noise and quantum fluctuation in the real world. And finally, we have the computational complexity consequences. Factoring will become easy. And there are other fantastic computational complexity consequences, like the permanent machines that I mentioned a bit earlier. Okay, so perhaps the last point I want to make is about experimentation. how my conjectures, how this matter is related to experiments, and in particular to attempts to build the quantum computers. And as I said, I should say that the most important way that my conjecture can be tested is via the ongoing attempt to create very stable qubits based on quantum error correction. So the expectation of researchers based on the theory as they understand it now is that once you have stable gates and qubits, then you can group them together and create a quantum computer, and this allows you to create via quantum error correction much higher, much more stable qubits. And my conjecture goes directly against this idea. And this is something which is experimented as these days by several groups of researchers. People are trying to build highly stable logical qubits based on surface codes or based on other codes, based on other ideas from good but not perfect physical raw qubits. And for example, John Martini has a program where he expects to create stable qubits based on 35 stable logical qubits based on 35 raw qubits in the next few months, maybe weeks, and then much more.
How many stable qubits?
35. So one stable. One stable qubit based on 35 raw qubits. And this is experiment that has to be completed in the next few days. And he thinks that in the next couple of years he'll be able to build one stable qubits based on about 120 physical qubits based on surface code, distance 5 surface code, which will be much more stable than the original qubits. And perhaps in 5 years something even fantastically more stable based on 1,000 physical qubits. Now, even I expect that my conjecture will show up even for the 35 qubits experiment. And certainly if there will be a success in the 100 qubits experiment, this will smash my conjectures to pieces. But one can also expect that experimental expectations will not be fulfilled, and that similar to the case of the famous experiment of Michelson and Morelli, they expected to see differences in the speed of light in different directions, and they didn't see it, which was quite important. Then these attempts by Martini and by other researchers to build logical qubits based on raw qubits and to implement error correcting codes for that will not be successful. Now there are, I should say that the success and failure, there's not just one bit of information. We'll be able to learn from this experiment a lot of more things. We'll be able to tell if errors are positively correlated, if we'll be able to test if there is a error synchronization that is predicted here. So there are, this experiment will give much more detailed in order to examine the suggestions put forward in this lecture. Perhaps one more place which is sort of a side issue, but a very sharp distinction between my models and the physical model for errors. So this is not the computer science models. They allow some adversary, so they are not physical to start with, but there are several papers on Hamiltonian models. And one of the surprising thing about these Hamiltonian models is that you have noise, but the noise itself is very robust. So for example, the amount of noise, the rate of errors has some Gaussian behavior. So you can predict the error rate is concentrated and the fluctuations are Gaussian, sub-Gaussian. Now, I found it very hard to believe that this is the behavior of noise in interacting quantum systems. And I think that this can be refuted even when the interactions are very weak, even in digital memories. So this is another point that can be tested experimentally. So let me summarize by saying that quantum fault tolerance represents a major phase transition for noisy quantum systems. Finding the appropriate mathematical tools to model and understand the nature of this phase transition, the quantum fault tolerance barrier, is important to the understanding of quantum noise and approximations in quantum physics. My expectation is that the ultimate triumph of quantum information theory will be in explaining why quantum computers cannot be built and drawing major consequences for quantum physics. So thank you. So this is the end of the lecture, of the formal part of the lecture. Now after this part we have another part which is sort of more entertaining part, which showed various pictures and some entertaining quotes from the debate. Okay, so this is the additional part for the lecture, and I will show some picture related to my lecture on why quantum computer cannot work, the quantum computing debate, and related stuff, and a few unrelated things. So we are recording it. This is the first ever production of the Simon Institute Recording Lab, and here in the audience is Tzlil. Well, you will not be able to see it if you sit there. Oh, you see here. Oh, okay, good. So here are a few pictures related to quantum computer, my quantum computation work. And here is, just to start, this is a picture of me and Aram Haro. We had the entire debate without ever meeting each other. And then a few months later we met at MIT, which was very nice. And here we shake hands between these brackets, which are so typical to quantum mechanics and make no sense to anybody else. So this is this picture. The next picture is taken in 2005. This is from Mittag Leffler Institute near Stockholm, and this is when I started my work in quantum computation and quantum fault tolerance. And here I am with two French mathematicians, Xavier Vienneau and Alain Lascaux, who passed away a few weeks ago. And we are in a very untypical snowy Stockholm. So a few months after I started working, I invited to Jerusalem essentially the other researcher working in the negative direction of regarding quantum computers, who is the physicist Robert Alinsky. And he is the guy here on the right. What is really different here, it's not like a mirror, it's really the right side. So you see, if I do this, it's really a very strange feeling, because anyway. So this is Robert Alinsky, and here are Dorita Aronov and Michael Benor, who are one of the teams for the threshold theorem, and are very famous computer scientists and quantum information people. And Michael was essentially in my year, and we studied together since we were kids. And Dorit was an undergraduate student. Now, Robert Alinsky, I met him first in Jerusalem, and I met him several times in Israel. Only last summer I visited him in Poland. So when I gave a talk there, I prepared a special slide to show our attempts to climb the mountain of quantum computers, just because it is not there. And often Robert and I are referred as skeptics. I like to think about myself as a quantum information researcher, but maybe it's a correct description. I remember that I wrote a book about Gina, and a few days ago Luca Tervisan referred to Gina as a troll, which I took as very offensive, but then Tzlil also said that she's certainly a troll, so maybe she is a troll. And also here, there are some pictures of me and Robert in Gdansk. Yeah, did I say Poznan? No, I visited him in Gdansk, and we look skeptical. Yeah, I mean, this is not stage. Our face have a clear skeptical impression. Yeah, we can see it. Yeah, yeah. So here we look in the same direction and we look skeptical. And here we look in opposite direction and we also look skeptical, right? And yeah, maybe we are skeptical, skeptics. And here we have this skeptical smile, but I think the skeptical impression is clearly evident. So actually, before I started working in quantum computation, maybe 3 years earlier, I heard a lecture at Yale by Michel Devoret. The name of the lecture was The Quantum Computer Miracle or Mirage. I don't know precisely what he meant. I mean, both miracle and mirage are sort of counter to the reality. In any case, I remember I saw this lecture and I thought with Ravi Kannan, and I thought there that maybe not enough people are working on the mirage direction. Now, this picture is utterly unrelated, but it's such a good picture that I wanted to show you. This is Avi Vigderson and Oded Goldreich when they were just graduating from the Technion. In the early days of my quantum computing interest, I took part in Dave Bacon blog, and he was a little bit offended by my negative views. So to cheer him up, I linked to my name the following page, which showed my philosophy regarding the topic. The hypothesis of fault-tolerance quantum computing is going strong, and here we see Dave skiing, I suppose near Seattle, but other possibilities should also be considered. And here you can see my first surfing attempts, and also last, I must admit. Actually, this is again an unrelated picture. This is Gadi Kozma. Do this. He is giving a lecture. This was in the Midrasha a few years ago in memory of Oded Shram. And this is also unrelated, but it looks that it's suitable for Israeli public relations. You see here the Wailing Wall, the flag of Israel, Terry Tau, and me. And here, 8 years later, again, the same people, maybe in a different permutation, Michael Ben-Or, Robert Aliski, Dorita Aronov, and me, also in Jerusalem. Okay, this is Michel Diakonov, who is also very skeptical. He's a physicist, skeptical about quantum computers. He is also skeptical that being skeptical is any use, so he doesn't do much research in this direction. And this is Scott Aronson, who is also very active in the scene. He has a very active blog, and he likes to discuss conceptual issues, and we will come across his name soon. And here is John Preskill. He was also part of the debate, and he's a prominent physicist working, among other things, or recently mostly on quantum computation, topological quantum computing. And here is Peter Shor, who is the father of both Shor algorithm, quantum error correction, and quantum fault tolerance. Here's again, not entirely related, but this is me and my children, my family, except Mazi, who is not here. So this is me on the left. Next is Lior, my son, Neta, my daughter, who is getting married in three weeks, and Neil, who is Chagai, my son's partner, and Eran. So I prepared some kililish for Neta, but it didn't work. So you know what kililish is?
No.
Kililili. I know this.
Yeah.
Okay. Okay. So now a few entertaining moments from the debate. So certainly one of the most exciting parts was this blog post by Scott Aronson. Whether or not God played dice, I do. So Scott said, for better or worse, I'm now offering $1,000 award for a demonstration convincing to me that scalable quantum computing is impossible in the physical world. This award has no time limit other than my death and is entirely at my discretion. It goes without saying that if I will be eligible to any part or to all of this amount, I will not take any dollar from Scott. Every dollar I earn will go back immediately to Lily's college education fund. Okay, so here are also few passages from the debate, a bit entertaining, a bit educating. So the first is from Aram's very first post about the distinction between quantum computers and classical computers. And indeed, Aram raised the important question, if quantum computers are impossible, how is it possible that classical computers are possible? Okay, I mean, I cannot deny as much as I want that classical computers, the classical computation is possible. But here is what Aram wrote, February 6, 2011. If you want to prove that 3-sat requires exponential time, then you need an argument that somehow doesn't apply to 2-sat or XOR-sat. And if you want to prove that the permanent requires super polynomial circuits, you need an argument that doesn't apply to the determinant. And if you want to disprove fault-tolerant quantum computing, you need an argument that doesn't also refute fault-tolerant classical computing. Sounds like not a bad analog, right? Okay, let's think about it. This is February, we'll come to it sometimes later. Okay, here is something I wrote to Aram. I wanted to emphasize the fact that my distinction between, what I call the quantum fault-tolerant barrier, is meaningful even if quantum computers can be built. So here is what I wrote. When Aram's grandchildren will ask him, Grandpa, how was the world before quantum computers? He could have replied, I hardly remember, but thanks to Gil, we have some conjectures recording the old days. And then he will state to the grandchildren conjectures 1 to 4 and the clear dividing line in terms of conjecture C. And the grandchildren will burst in laughter about the old days of difficult entanglements. Yeah, and they're also very intelligent grandchildren if they know about entanglement. So the context of this was conjecture C. So one of my conjectures was shot down by Aram Haru and Steve Flemia. They found the counterexample. And I wrote a heartbreaking eulogy for conjecture C, which is here. When Aram wrote to me in June 2011 and expressed willingness to publicly discuss my paper, my first reaction was to decline and propose having just private discussions. Even without knowing Aram's superb track record in debates, I knew that I put my beloved conjectures on the line. Some of them, perhaps even all of them, will not last. Later, last December, I changed my mind, and Aram and I started planning our debate. My conjectures and I were fully aware of the risks, and it was conjecture C that didn't make it. A few words about conjecture C. Conjecture C, while rooted in quantum computer skepticism, was a uniter and not a divider. It expressed our united aim to find a dividing line between the pre- and post-universal quantum computer eras. Here's another nice part of the debate. It's called Jesus. Aram, somewhere around June. Here is what Aram wrote. However, the task of skeptics is now a difficult one. Attempting to give a theory that would exclude quantum computers while keeping quantum mechanics reminds me of the famous saying of Jesus. It is easier for a camel to pass through the eye of a needle than for a rich man to enter heaven. What I like about this quote is that it expresses the idea that something may be in principle possible, a rich man going to heaven, but there are so many difficulties along the way, how one acquires one's wealth, the fact that it hasn't been given to those in need, etc., that one is left with either the vivid impossibility of the camel or the painful alternate reading of trying to thread rope made of hemp or camel hair. So this was a sort of a highlight of the debate, but it was not clear that this can be a basis for a very thorough scientific discussion. Okay, let's get back to Aram's 2-sat and 3-sat analogy. So here is the reply, which came in September, so it was about 9 months. So Aram offered he said, if you want to prove that 3-sat require exponential time, then you need an argument that somehow doesn't apply to 2-sat or XOR-sat. This is correct. Proving that 3-sat needs exponential time requires an argument that does not apply to 2-sat and XOR-sat. And today, after many years, we do not have such an argument. But this does not mean that we should believe that 3-sat behave like 2-sat. So this analogy, it's not a bad analogy, but it's go precisely in the other direction. We still don't understand why, or fully understand why 3-sat is hard and 2-sat is easy. But nobody sensible believes that because we don't understand it, we will think that 3-sat is easy as 2-sat. And essentially, this is what Aram analogy suggests. And in fact, there is one more important thing. Perhaps we don't understand the basic principle for why 3-sat is difficult, but we do understand that the difficulty of 3-sat by itself is a very important principle that reflects on all of our knowledge of computation. And a similar thing may well happen for the difficulty of quantum fault tolerance. Okay, here is one of Aram's last comments. It's sort of amusing, and it has to do with some serious point, but it also has some entertaining part. Okay, November 2012. The reason I think that the classical computer and quantum computer emulations are not so far apart is that, and now Aram described the quantum case, and he continued, the same story can be told about the exponential time classical emulation, except that now the encoding is no longer a unitary or indeed linear map. I agree, said Aram, that the quantum emulation feels closer to the original physics than the classical emulation does. But this seems like rather imprecise statement and not something that can be formalized. So on the serious note, I disagree with Aram. I think not only that we should try to formalize such distinctions, it's our job as mathematicians to formalize mathematically such distinctions. We can formalize important, fundamental thing, and we can formalize not so important things. But the funny part about this is that in the last sentence, Aram says that it is not something that can be formalized. But in one sentence above, Aram offers a formalization. He says that in one case it is linear, and in the other case it is not linear. This is indeed a formalization. So this is sort of funny, I don't know. Perhaps for mathematical nerds it can be funny. So a similar thing can be said about the very first words of Aram in the discussion. Here is how Aram started the debate. He said, there are many reasons why quantum computers may never be built. We may fail to bring the raw error rate below the required threshold while controlling and interacting large number of qubits. We might even find an efficient classical simulation of quantum mechanics. The one thing I'm confident of is that we are unlikely to find any obstacle in principle to building quantum computers. So here my position is entirely opposite. If we will not be able to build quantum computers forever, then one thing I'm sure about is that we will be able to find the principle, the modeling principle to make the distinction between quantum computers and classical computation. This distinction, this mathematical distinction, may represent a fundamental law of nature, it may represent an engineering obstacles, but we should be able to do it. And as mathematicians, this is essentially our job. Okay, so this was the end of our extra part of the lecture. Okay, we are reaching the end of this presentation. I gave this lecture in several places and there were very good comments and questions, and I will mention a few of them. Perhaps before that, let me mention that when I gave the lecture here at the Simons Institute, just before the last slide, the summary slide, a person entered the room and sat down, and when I finished, he asked the first question, which seemed related to the lecture, but I couldn't fully understand it and answer him, and he took it rather well. But there were a lot of other interesting questions and suggestions, and let me perhaps mention a few of them. So one surprising question that I was asked is what I would prefer if it was up to me, if quantum computers can or cannot be built. And I think my preference would be that quantum computer could be built. So building quantum computer promise a lot of fruits for science, for physics, for technology, and also it is quite interesting that the possibility of quantum computer give not only researchers in this field or scientists, but also layperson give a lot of hope to these people. Another question that I was asked is, isn't it the case that my models are assuming that quantum fault tolerance is not possible, or starting from the assumption that quantum fault tolerance is not possible, and by some sort of reverse engineering trying to describe the noise models which support these assumptions. And the answer is absolutely yes. This is precisely what I'm doing. Another question that was raised in the talk here was about the title. Isn't the title "Why Quantum Computers Cannot Work," isn't it too strong? And of course, this is something which I explain amply in the lecture itself. As in the theory of computing, we try to examine even very hypothetical possibilities. There is a famous lecture by D. Karp, which was where he entitled "If pigs could fly, then cows could whistle," and trying to find the relation between assertions in computational complexity, which both are very unlikely. But I should emphasize that here I regard the possibility of quantum computer as rather remote, and I think that eventually it will turn out that quantum computation, superior quantum computation and quantum fault tolerance are indeed impossible. Another question that I was asked is if indeed the no quantum fault tolerance is a basic physical principle, say principle of thermodynamics, how come that it was not discovered before? And there are several things to say about it, but perhaps a main thing to remember is that quantum fault tolerance and quantum error corrections are newly discovered notions. And arguably, the importance to physics from quantum fault tolerance and quantum error correction is even larger than the importance to physics coming from quantum computation. And I think the importance of quantum fault tolerance to physics is similar to the importance of non-deterministic computation in complexity theory. Their importance is that they cannot be achieved. Now, talking about thermodynamics, perhaps I will end with a sort of speculation, is that the notion of time emerges as a real physical entity rather than a mathematical convenience from the interface between quantum mechanics and thermodynamics. And indeed, the topic of this lecture and the study of quantum noise is largely related to this inference. So these were a few questions, and let me end by thanking various people who supported this research as well as this production. So first I would like to thank my academic home, the Hebrew University of Jerusalem, where I am as a student and later as a faculty in the last 42 years. And I would like also to thank my academic home away from home, where I held a part-time visiting position, which is Yale University. And I would like also to thank several granting agencies which support my research, the ERC Advanced Grant, as well as grants from BSF, ISF, and NSF. And thanks again to the Simons Institute and to Ivan, who helped with this production. And last but not the least, I would like to thank Tzlil Shram, who also helped with this production. And thank you, Tzlil. עכשיו צריך לערוך את זה.
נכון.
טוב, להגיד היי לכולם.
אני ואתה נשנה את העולם, אני ואתה אז יבואו כבר כולם, אמרו את זה קודם לפניי, לא משנה, אני ואתה נשנה את העולם. אני ואתה ננסה מההתחלה, יהיה לנו רע, אין דבר, זה לא נורא, אמרו את זה קודם לפניי, זה לא משנה, אני ואתה נשנה את העולם.